Did you know that just 2 years after the Wright brothers took flight, a thought experiment about watching a radioactive atom from a spaceship changed our understanding of the universe itself? Thought experiments have been the cornerstone of theoretical physics, serving as a powerful tool for scientists to explore the realms of the impossible and the unknown without leaving their desks. In this video, we delve into the cornerstone thought experiment of theoretical physics, the thought experiment behind the most famous equation of our lifetimes, E equals mc squared. Then, we'll take a look at modern science, discuss these assumptions and implications for our current theories, and finally, develop the Tobe, a theory of basically everything. Hello and welcome. I'm thrilled to have you join me on this exploratory journey. Context is key to understanding, so let me set the stage by sharing a bit about myself and what led me down this path. My academic training is in chemical engineering, mathematics, and I have a Master of Legal Studies in Energy Law. My professional journey started in oil and gas. My dad taught me to leave everything better than when I found it, and when I realized I could not do that in oil and gas, I quit. For the last 2 years, I've been pushing the boundaries of hydrogen combustion technology in pursuit of net zero environmental impact, designing oxy-hydrogen boilers. I quickly learned that this transition wasn't just a career move. It was a profound learning experience that challenged my conventional understanding of energy, cultivated during my university years. Hydrogen stands as the paradigm of a perfect fuel, embodying an ideal that balances efficiency with environmental stewardship. Its combustion process, elegantly simple, produces water as its sole byproduct, leaving behind no emissions to mar our planet's health. Moreover, the utilization of hydrogen in fuel cells presents an opportunity for generating electricity with remarkable efficiency through its reaction with oxygen. Yet, this beacon of potential is dimmed by a fundamental flaw, the challenge of its generation. At present, we find ourselves at a crossroads, torn between the economically driven production of hydrogen through fossil fuels, bearing the weight of associated emissions, and the environmentally conscious, yet energy-intensive green production via electrolyzers, which demands quintuple the energy input. Throughout my career in hydrogen combustion, the prohibitive cost of achieving net zero emissions loomed large, a persistent hurdle that spurred my quest to develop a more efficient production method. 20 months ago, I decided to go all in, liquidating my retirement accounts to fund exploratory research and prototype development. At my day job, I was burning hydrogen, but from 5 p.m. to 2 a.m., I was making it. In the summer of 2023, I had a breakthrough, beating the efficiency of every electrolyzer on the market by, like a lot. I couldn't believe it. It seemed to be the perfect device. It didn't even generate waste heat. And after sinking a small fortune into electronic testing equipment, it became apparent. It operated fundamentally differently in a realm of physics that I could not quantify. This video is a culmination of these insights, gathered over 2 transformative years, represents my hope to illuminate a path towards a sustainable, renewable future. Let's embark on this journey together with open minds and a shared vision for a brighter world. In creating this video, my intention is not to undermine the groundbreaking contributions of Einstein. After all, Einstein's theories have paved the way for monumental advancements, ranging from solar power to atomic weapons, illustrating the profound impact of his work on both our understanding of the universe and practical technological developments. Echoing the spirit of Einstein's own words, in the following, I wish to present the line of thought and facts which have led me to this point of view, hoping that this approach may be useful to some investigators in their research. My aim is to foster a constructive dialogue that builds upon these foundational discoveries. It's disheartening to observe how some of the scientific community criticizes Einstein for his supposed missteps, neglecting the essence of scientific inquiry, an open mind. Successful science thrives on curiosity, openness to new evidence, and a willingness to reevaluate long-held beliefs. This video is a tribute to that spirit of inquiry, seeking not to fault the giants upon whose shoulders we stand, but to explore how their ideas interact with and are enhanced by contemporary discoveries. First, let's delve into some pivotal discoveries that have expanded our understanding of physics beyond the foundations laid by Einstein, offering new perspectives on his thought experiments. Firstly, the existence of the neutron. Unknown until James Chadwick's groundbreaking discovery in 1932, opened a new dimension in particle physics. Neutrons possess intriguing properties, such as the ability to oscillate between protons and antineutrons, challenging and extending our understanding of particle physics. Shortly thereafter, we also discovered quantum spin, The Stern-Gerlach experiment revealed how placing an electron or atom within a magnetic field sorts the particles into multiple groups based on their spin. This phenomenon, foundational to quantum mechanics, has been further elucidated with advancements in controlling spin using lasers and acoustic vibrations, demonstrating the intricate control we now have over quantum states. In the 1950s, our exploration of the universe's electromagnetic spectrum took a giant leap forward with the discovery of solar wind and the cosmic microwave background radiation, significantly enhancing our cosmic comprehension. The field of plasma physics, taking hold in the 1920s, owes much to Irving Langmuir's characterizations. His characterizations laid groundwork for our understanding plasmas and particles in the heliosphere and magnetosphere. This area of study has been vital in space exploration and understanding our universe's larger electromagnetic interactions. The invention of antennas and the evolution of wireless communication has revolutionized our ability to transmit and receive information over vast distances, fundamentally changing our interaction with technology and each other. A monumental advancement in our understanding of the universe came with the discovery of gravitational waves by LIGO in 2015, proving Einstein's century-old prediction and offering us a new tool to observe cosmic events across the vast expanses of space. Moreover, our scientific literacy and the precision of our instruments have both seen remarkable improvements. We've developed techniques sensitive enough to detect the force exerted by a laser pointer, and have gained deeper insights into the fundamental forces, including van der Waals forces and photon scattering, further enriching our understanding of the microscopic interactions that govern our universe. Advancements in imaging techniques, like Schlieren imaging, have unveiled the unseen world around us, providing a striking visualization of phenomena such as shock waves and temperature gradients. Each of these discoveries and advancements represents a leap forward in our comprehension of the universe, challenging and expanding upon the seminal theories proposed by Einstein. As we continue to explore and understand, we stand on the shoulders of giants, pushing the boundaries of what is known and venturing into the vast unknown with an open mind and insatiable curiosity. To grasp the significance of contemporary advancements on thought experiments that have been foundational for over a century, we'll begin by closely examining the original setups of these experiments. Our exploration will draw upon insights from floathead physics, particularly his video titled, Why the Speed of Light Results in E = mc squared, which offers an intuitive breakdown on Einstein's theoretical constructs. In this analysis, floathead physics highlights Einstein's pioneering assumption. It's conceivable to move with a constant velocity in relation to the vacuum, thus requiring no acceleration. This premise underpins several key properties attributed to the speed of light. Its ability to propagate through a massless medium and its invariant speed. Despite traditional electromagnetic theory suggesting that wave propagation requires a medium and results from accelerating charges. Furthermore, Einstein speculated that the Doppler effect, which accounts for the increased energy of photons, operates in a massless medium, implying that this energy must originate from the emitting atom itself. These assumptions collectively led Einstein to his revolutionary conclusion that the fundamental aspects of our universe, time, space, and motion, are all relative. In this video, we'll delve into these assumptions, examining them through the lens of modern physics. Our goal is to discern how current scientific understanding might challenge or refine these enduring principles that have shaped our view of the universe for over a century. In our journey to unravel the impact of modern advancements on century-old thought experiments, we'll focus our lens on three pivotal topics. These discussions will not only deepen our understanding of the theories proposed by Einstein, but also challenge us to view them in the light of contemporary scientific discoveries. Our first dive is into the concept of relative motion. While I find common ground with Einstein on the notion of relative motion, it's fascinating to note that his perspective here seems to echo Newton's discourse on absolute motion, famously illustrated through his bucket experiment. This parallel invites us to explore how the idea of motion, whether absolute or relative, has evolved from Newton's time to Einstein's era and how it continues to adapt in the face of new scientific findings. By examining the foundational principles and the experiments that demonstrate them, we'll gain an insight into the continuous dialogue between the past and present understandings of motion. Next, we turn our attention to the conservation of energy, a principle that remains steadfast in the physics playbook, a principle that I'm not challenging. To bring this concept into the context of modern physics, we'll introduce the innovative tool of mass energy time diagrams. Before we dive deep, a brief overview of base units will set the stage, ensuring we all share a common language for the discussion. These diagrams offer a unique perspective on energy conservation, weaving together mass, energy, and time into a coherent visual narrative. They allow us to visualize how Einstein's revolutionary equation, E equals mc squared, functions within the broader tapestry of physics, and how it aligns or conflicts with our current understanding of energy conservation. Our final topic brings us to the speed of light, a constant that serves as a cornerstone of modern physics. Revisiting concepts such as the solar wind and the cosmic microwave background of the observable universe will provide us with a richer context to appreciate the significance of the speed of light. These phenomena, integral to our understanding of the universe, underscore the consistency of light speed across various cosmic events and settings. By examining the role of the speed of light in the vast expanse of the universe, we'll explore how this constant informs our understanding of space and time, and how recent discoveries might offer new perspectives on this fundamental aspect of physics. Through these topics, we aim to bridge the gap between Einstein's revolutionary ideas and the relentless march of scientific progress, all the while appreciating the intricate dance of ideas that propels us towards a greater understanding. In our exploration of the foundational experiments that have shaped our understanding of motion, we begin with a classical experiment, Newton's spinning bucket. This experiment involves suspending a bucket filled with water by a cord, twisting the cord to induce rotation, and observing the behavior of the water. Initially, as the bucket begins to spin, the water remains still, its surface flat, but as the water catches up with the bucket's motion, its surface adopts a concave shape. Newton interpreted this concavity as evidence of absolute rotation relative to an absolute space. He posited that the centrifugal force responsible for the water's concavity could only be explained by the existence of absolute space. This, according to Newton, demonstrated the objective reality of forces like gravity and centrifugal force, anchored not in relational terms, but in the context of absolute space. This stance, however, posed a challenge to the principle of relativity, implying that motion can indeed be measured in an absolute space, independent of other objects. Contrary to Newton, Ernst Mach argued that all motion is relative, contending that the water's concavity should be understood in terms of its motion relative to the distant stars in the entire universe, a concept that significantly influenced Einstein's theory of relativity. Transitioning to the modern context, we consider an updated version of this experiment conducted aboard the International Space Station, where many terrestrial influences are minimized. In this iteration, the bucket, equipped with a lid and spun by an astronaut, behaved differently from its terrestrial counterpart, rotating over its longest axis. This divergence in behavior between the terrestrial and space-based experiments challenges both the notions of absolute motion and motion relative to distant celestial bodies, suggesting instead that motion must be understood relative to its immediate surroundings. Interestingly, the addition of a lid on the bucket, a variable absent from Newton's original setup, does not alter the foundational results. The transition from a flat water surface to a concave shape upon rotation remains consistent, affirming the relative nature of motion within the bucket's context. However, the absence of water, as seen in solid bodies or buckets without water aboard the International Space Station, does not replicate this behavior, underscoring the complexity of motion and its relative characteristics. The distinct behaviors of the terrestrial and space-based buckets suggest that while motion is not absolute, it cannot be solely relative to the vast expanse of space or celestial bodies. This finding propels us into a deeper inquiry into the nature of motion, emphasizing its relativity to the immediate environment, an insight that lays the groundwork for further discussions on the conservation of energy and the speed of light. In summary, the motion within these experiments, whether of water in a bucket or the bucket itself, is intricately linked to its surroundings, be it the bucket structure or the air it displaces. As we proceed, this understanding will serve as a cornerstone for unraveling the complexities of motion, energy, and light in the universe. Now, we will begin to explore the intriguing concept of mass-energy-time diagrams, a visual tool presented here as a thought experiment that helps us explore the relationship between mass, energy, and the effects of motion. Traditional physics teaches us that objects possess more mass when they hold potential energy, as seen in a compressed spring compared to an uncompressed one, or a hot cup of coffee versus a cold one. However, this principle seemingly does not apply to objects in motion in the same way due to the relativity of motion. Explicitly, we're proposing a perspective where the relativity of motion does not exempt an object from having a measurable effect on its mass due to its motion. Considering the universe's nature, where everything interacts with its surroundings, no matter how minutely, every motion instigates a level of interaction, potentially impacting the object's mass. We begin by revisiting the Doppler effect, traditionally associated with perceived changes in frequency and energy for sound waves. Contrary to this perception-focused understanding, we argue that the energy dynamics of both sound and electromagnetic waves reveal genuine changes in energy states. obscured by the complexity of particle interactions. To examine this, we'll look at the increase in energy observed with the Doppler effect in sound waves, which has long been considered a perceptual phenomenon. Noting that in our control of quantum coherence, or manipulating spin states, rests on altering spin with lasers and acoustic and electromagnetic waves, meaning this should no longer be considered a perceptual phenomenon. A deeper dive into the interactions at a particle level suggests a mechanism. When examining the potential energy diagram of two particles as they approach each other, we observe a significant insight. Initially, as the particles come closer, their overlapping fields create a dip in potential energy, indicative of an energetically favorable state. Yet, as they overlap further, this energy sharply increases, reflecting a strong repulsive force. This behavior of particles under compression, which is fundamental to the nature of waves, reveals a hidden aspect of energy dynamics, sound waves, by compressing particles effectively, bringing them closer in proximity, momentarily placing them in this dip or lower energy state. Notably, no energy is released during this process of compression. Instead, it's as if the energy is stored, hidden in this compressed state of the particles. This observation aligns with our mass energy time diagrams, suggesting that while potential energy may seem lower, no actual energy loss occurs. The system's total energy remains conserved. This refined understanding challenges conventional perspectives on energy behavior and wave propagation, especially for electromechanical waves, such as sound, and as we will discuss later, gravity. It underscores the importance of considering particle interactions to fully grasp energy dynamics. In this light, both sound and electromagnetic waves, through their respective mechanisms, lead to real changes in energy states, changes that are critical to our understanding of energy conservation and the mass-energy relationship. In delving into Einstein's work, we encounter a puzzling scenario. Observations of blue-shifted and red-shifted light suggest that these waves possess more energy than their initial state. How can we reconcile this with the principles of energy conservation? The answer lies in closely analyzing the phenomena within the context of their surroundings, including interactions like the solar wind plasma. Einstein created relativity to solve the energy balance of this problem. However, with including solar wind plasma in this model, we can solve his same energy balance via already understood particle interactions, instead of warping space and time. We do this by drawing a conceptual box around the rocket, performing an energy balance against its surroundings. We uncover that any motion necessitates a force, however negligible. This force, indicative of energy expenditure, offers a means to determine a motion's impact, supporting the argument that motion indeed influences mass. Consider the simple act of an athlete throwing a ball. At the moment the ball leaves the athlete's hand, it's at its most massive, carrying the energy imparted by the athlete. As it travels, it loses energy due to gravity and air resistance, evidenced visually through Schlieren imaging, which captures the convective air current generated by the ball in motion. This loss of energy, or interaction with the environment, suggests a change in the ball's mass, directly tied to its state of motion. In our journey to uncover the mysteries of mass-energy-time relationships, a fundamental exploration into units and the permeability of free space becomes essential. By deconstructing derived units back to their base units, we gain a deeper insight into the underlying physics that govern our universe. Let's embark on a thought-provoking exploration, starting with resistance and current, and extending our understanding to the permeability of free space. Consider, for example, resistance, traditionally expressed in ohms, with true units in terms of volts over amps. By analyzing the true units with respect to its physical formula, which is dependent upon length per area and the material's resistivity, we uncover a more nuanced understanding. Similarly, when we examine current, defined as charge per time, an intriguing comparison emerges. Charge relates to distance, current to velocity, and the derivative of current to acceleration. This analogy opens a new window into viewing electrical phenomena in terms of fundamental physical concepts, especially when we consider that charge is just electrons times a constant. Armed with this understanding, we turn our attention to the permeability of free space, a value deeply ingrained in electromagnetic theory. By dissecting this constant into its base units, we reveal a compelling narrative. Acceleration, a concept at the heart of motion and force, emerges naturally from this analysis. This insight not only enriches our understanding of electromagnetic phenomena, but also underscores the interconnectedness of all physical quantities. To concretize these concepts, let's consider a simple yet illuminating home experiment. By quantifying the force between two current-carrying wires, we witness firsthand the emergence of a physical force, a manifestation of the principles we've discussed. This experiment not only demonstrates the real-world implications of our theoretical exploration, but also highlights how acceleration, and therefore force, materializes from the fundamental interactions described by the permeability of free space. Through this exploration of base and derived units, and the detailed examination of the permeability of free space, we've traversed the path from theoretical foundations to practical demonstration. This journey illuminates the profound truth that fundamental physical quantities, whether discussing resistance, current, or the very nature of force and acceleration, are deeply interwoven, each shedding light on the others. Our exploration not only advances our understanding of physics, but also invites us to ponder the beautifully complex tapestry of the universe's fundamental principles. As we venture further into our exploration of physics, we confront one of the universe's most intriguing phenomena, the speed of light and its electromagnetic interactions. Drawing from our previous discussions on the permeability of free space, we embark on a journey to unravel deeper mechanics governing the speed of light, challenging conventional perceptions and revealing the intricate dance of electromagnetic forces. Beginning with our derived equation for the permeability of free space, we encountered the absolute value of the natural log of current, a significant step that lays the groundwork for understanding light's behavior. By integrating this equation, we draw parallels with well-known relationship in physics. The product of the inverse of permittivity and permeability of free space equates to the speed of light squared. This relationship is pivotal, as it implies that the permeability of free space dictates an oscillation between positive and negative accelerations for the electromagnetic waves, offering a profound insight into the nature of light itself. Traditionally, light is perceived as traveling at a constant velocity without an acceleration vector. However, our analysis suggests that a radical reinterpretation. Light experiences rapid oscillations between positive and negative accelerations. This oscillatory behavior results in the observed constant velocity of the speed of light, a revelation that also reshapes our understanding of electromagnetic propagation, but a revelation that is also self-consistent with our understanding that all electromagnetic radiation requires an accelerating charge to propagate. The question then arises, why does light maintain its speed in mediums like air, despite factors like air resistance? The answer lies in the concept of impedance matching, a fundamental principle that ensures efficient transfer of energy in electromagnetic systems. Viewing our universe through the lens of antenna theory, we discern a pattern of energy absorption, emission, reflection, and storage. This perspective allows us to model celestial interactions, such as those between the sun, solar wind, and plasma, and the Earth, as complex antenna systems. These systems, through their inherent impedance matching, maintain the constant velocity of light across different media, ensuring the harmonious transmission of electromagnetic energy throughout the cosmos. In our quest to decode the mysteries of the universe, the analogy of the universe as an antenna system opens up a fascinating vista of interdisciplinary research, blending plasma physics with electromagnetic theory to shed light on celestial dynamics. This perspective not only challenges conventional views, but also harmonizes disparate phenomena under a unified framework. An emerging area of research, reconfigurable plasma antennas, provides the foundation for reimagining cosmic interactions. Plasma's unique properties, such as its ability to form precise connections between cathodes and anodes, integral to technologies such as plasma etching, suggest a refined understanding of solar emissions. Advancements in understanding plasma, the solar wind characterized by its remarkable speed and temperature, introduce a paradigm where the sun's emissions, far from being indiscriminate, engage in precise interactions with surrounding cosmic matter. Plasma's exceptional conductivity, which literature often considers infinite, reveals that charge predominantly resides on the surface of conductors. This insight into plasma's behavior underscores the conceptualization of vast plasma antenna system, bridging the Earth and the Sun. Through geometric-based antenna analysis of the system, we uncover correlations with known frequencies in physics, such as the 2 MHz frequency associated with gravity waves, and the 7.5 Hz frequency of the Schumann resonance, the Earth's natural resonant frequency. Drawing parallels with everyday phenomena, such as microwaving a grape, we observe striking similarities in the energy and temperature distributions when compared to terrestrial thermal activity. This analogy extends beyond superficial resemblance, proposing a more accurate explanation for the Earth's core heat and magnetic fields, traditionally attributed to radioactive decay and molten iron dynamics. Notably, this reevaluation aligns with the understanding that iron loses its magnetic properties above its Curie point, further validating the electromagnetic model of celestial interactions. The Earth's outermost atmospheric layer, the magnetopause, acts as a protective shield against solar wind plasma, which also functions as the near-field radiation zone of the Sun's antenna system. This shielding effect and physical dimensions of Earth and its surrounding space influence resonant frequencies that dictate not only terrestrial features, but also core heating and gravitational forces, drawing a striking parallel to the effects observed in everyday phenomena. This characterization of Earth's lower atmosphere, up to 80 kilometers, as influenced by the near-field effect of this cosmic antenna, elucidates why this region appears impedance-matched with the broader system. This understanding not only explains the presence of elements in their neutral diatomic form, but also offers a compelling explanation for the Earth's magnetic fields in its rotation direction, as predicted by the right-hand rule. On Earth, life thrives within the non-radiative field, a testament to the unique conditions fostered by these electromagnetic interactions. Near-field effects provide a compelling explanation for the quantum-scale breakdown of what we thought were universal laws. This perspective reveals the intricate dance of electromagnetic radiation in making celestial bodies observable, challenging our perception of space's emptiness, and offering a more nuanced understanding of celestial visibility and interaction. In this journey through electromagnetic theory of the universe, we have traversed the realms of plasma physics, electromagnetism, and celestial mechanics to reveal a cosmos far more interconnected and dynamic than previously conceived. By delving into the Sun-Earth interaction as a prototype for the vast plasma antenna system that spans the cosmos, we have unraveled a coherent narrative that harmonizes the principles of electromagnetic theory with the observable phenomena of our universe. From the intricate dance of the solar wind, plasma shaping Earth's magnetic fields, to the subtle yet profound mechanisms heating our planet's core, we have seen how electromagnetic interactions underpin the very fabric of cosmic existence. This exploration has not only challenged the traditional explanations that have long stood untested, but also offered a new lens through which to view the celestial and terrestrial alike. A lens that reveals a universe orchestrated through a symphony of electromagnetic interactions. The constant speed of light, once a mystifying phenomena, now reflects elegant interplay of forces and principles that govern the vast expanse of space, inviting us to reconsider what we know of light's behavior in its journey across the cosmos. As we conclude this voyage of discovery, we stand at the threshold of a new perspective on electromagnetic dynamics, one that underscores the universe's profound interconnectedness. This unified framework, which bridges the gap between mathematical abstractions and the tangible realities of our universe, enriches our understanding of fundamental physics and cosmology. It prompts us to view the cosmos not as a collection of isolated phenomena, but as a cohesive system, bound by the elegant laws of electromagnetism and animated by the ceaseless exchange of energy. As we draw this exploration to a close, I circle back to the genesis of this journey, a journey that began not in the vastness of space, but in the pursuit of a groundbreaking technological advancement, a method to generate hydrogen without emissions and also at unparalleled efficiency. This venture into new physics was driven by the necessity to understand and explain its extraordinary performance. These principles we've delved into today are not abstract theories confined to cosmic phenomena. They are fundamental truths that have profound implications right down to the molecular energy level. Let us be clear, this is not the introduction of a free energy device, but the unveiling of a radical new method of production, with the power to dramatically reduce emissions and slash energy costs by over an order of magnitude. The innovation lies in harnessing the principles of electromagnetic interactions in plasma physics to rethink energy generation at its core. A teaser to the underlying mechanics of this invention involves the electron configuration of neon. Modeling the atom as a dipole antenna with a corresponding number of dipoles mirrors its known electron structure precisely, hinting at a deep-rooted connection between our theoretical framework and practical energy solutions. But with great power comes great responsibility. The essence of this technology and the principles behind its operation will remain closely guarded for now, not out of secrecy, but to ensure its ethical application. Our vision extends beyond mere technological achievement. It encompasses a commitment to leveraging this discovery for the betterment of humankind, steadfast in our resolve to not commodify this innovation for the pursuits of war or destruction. Our comprehensive business plan is purposely not a roadmap to commercial success. It's a pledge to prioritize the well-being of humanity, ensuring that the fruits of this technology reach those who stand to benefit most. We stand at the precipice of a new era in energy generation, one where the potential for a cleaner, more sustainable future is within our grasp. For those intrigued by the possibilities and eager to learn more about how you can be part of this transformative journey, I invite you to watch our What's Next for Tobe Energy video. Together, we can redefine the future of energy, guided by the principles of science and a commitment to ethical innovation.